So here's kind of where we left off last time. If we have a stable extension, then E prime, which is a subgroup of the Galois group of F over K, it's Galois group of F over E, is actually normal in the Galois group, and it works the other way as well. That is, if you find a normal subgroup of the Galois group, then its prime is a stable intermediate extension. So this is the next result that I'm going to have. And let's see, we had this one. I believe we proved this one.
We were working on 8.2.16.
Right. So this one said that if K and E and F are, or I'm sorry, if F is Galois and E is stable, then E is Galois. Then E is Galois. Okay. And we got through this last time. So the next piece we're going to need here, and this is actually, the next one is actually, I think, is important for its proof because the proof tells you some stuff that I don't even really state here, but I'll talk about it when we get through it. Lemma. If you have a tower of fields, and you have that E is algebraic and Galois, over F, or I'm sorry, over K, then E is stable. Okay, so let's look at why this is true. Proof. Now, of course, what it means to be stable is if you have any element of the automorphism group of F over K and you apply it to E, then that automorphism still needs to leave this in E. We need to see why that's true. Now, suppose we have U and E. The fact that E is algebraic over K means that U is algebraic, and so it's got some minimal polynomial. So let U is algebraic with minimal polynomial. Let's call F of X in K of X. Okay, so it's got some minimal polynomial. Now, what I want to do now is, I almost did that. This is the list of the distinct roots in R. And right. So this is E is algebraic. I don't claim that there's any more than, I know there's one root, namely there's U. I don't claim that there's necessarily any more roots, but if there are, I will list all the ones that are different, right? So, um, the number of distinct roots is certainly less than or equal to the degree of the minimal polynomial, right? Now let's pick any automorphism of E over K. And I want to consider this polynomial. Now, what do I know? Right? So if I apply this tornado here to this thing right here, what it does is it permutes these roots somehow. So what does that mean? This means that it has to be g of x, right? Because whatever that tornado does, it plays a shell game with some of those UIs. Since they're all distinct, you don't have to worry about any kind of confusion there. It doubling up. It permutes all these roots and it gives you g of x. Hence, um, now since E is Galois over K, g of x is actually in kx. Because K is the fixed field of the group of all automorphisms, right? And so this means that this g of x, so in other words, when you multiply this mess out, what you get is a R degree polynomial, all of whose coefficients are in the base field of K. Um, f of x in kx must divide g as f of x is minimum. And hence, what can we conclude? F of x equals g of x up to a multiple of some alpha k that's not zero. Right? So in other words, if I demand that f of x be monic, then f of x and g of x are the same, because certainly g of x is monic, isn't it? Right? So what do we get from that? So what are our conclusions? Well, if the minimal polynomial of K of X, we've shown it turns out to be G. And so in particular, um, of U, uh, the minimal polynomial of U is has all distinct roots the roots are in E. Because remember, this tornado was in the Galois group of V over K, so it takes any of the UI, that's some UJ, which is still on U, because these U's were picked to be the distinct roots in A, right? Hence, uh, for all, uh, because when you apply an automorphism of F to any U in there, it has to go to another distinct root of that, well, it has to go to another root of that polynomial, which also is in E. And so sigma of E is in E. Everybody okay with that? Now it's actually important. We didn't demand this in the proof, but it's something that comes up, and this is going to be of importance later. By the way, what do you call a result that's kind of a spin-off of a, so here, this is kind of a fun English quiz for the day. This will be your $64,000 word. If you have something that's a consequence of a theorem, you call it a corollary. If you have something that follows as a consequence of a proof, it is a, anyone heard this one? So here's your $1,000 word for the day. Aforism of proof of lemma, whatever it was, 8216, is that all roots of f of x are, and this is the minimum irreducible polynomial, when E is Galois, are distinct. Right. So what we have from this, which is kind of interesting, so we're going to see that another equivalent characterization of Galois. So we know Galois is F is Galois over K if the fixed field of the Galois group of F over K is precisely K. Another way to think of this is if you have anything that's in F but not K, there's some automorphism that moves it. Another characterization that we're going to get of Galois later is a field extension is Galois if it's normal and separable. And I haven't defined what either of these are, but separable basically means that minimal polynomial, an element separable if when you take its minimal polynomial, it has all distinct roots. Okay. Any questions? All right. So here's one last limit that we're going to use, and I think this will tie everything together for us. Suppose you have the tower fields K and E and F, and an E stable, so it's a stable intermediate extension in the sense that any automorphism of F takes E inside of E. Then the quotient group modulo Galois group of F over E. We've seen for the case of stability that this is actually normal in this, so this makes sense. Is isomorphic of E over K. Well, that's big. Let me put it in play. Is isomorphic to the group of K automorphisms K automorphisms of E that are extendable to F. Okay. Let's go through a quick proof of this. So we want to let's define this map from the Galois group F over K to Galois group E over K. Okay, so what's the easiest way to this map? What's the easiest way to start with an automorphism of F fixes K and get an automorphism of E fixes K? Yeah.
Will we restrict it to E?
How about that? Let's just restrict it. Certainly, restricting the domain gives you an automorphism. Well, let's be careful. Here's what I know. I know when I restrict this, it's still going to fix K. No problem there. Also, whatever this thing is going to be one-to-one and onto its image. What's the real thing here? The real thing is why is this actually an automorphism? See, it's supposed to go to the Galois group of E over K. Why is it an automorphism of E? Because E is stable, right? The image of this is a subgroup consisting of Galois group of E over K. Well, what is it? Is the subgroup of Galois group of E over K consisting of automorphisms. Well, let me be careful here. K automorphisms of E that are extendable. And of course, since they take that form, we know automatically they're extendable because, after all, they came from an automorphism of E. The kernel of F well, yeah.
I don't see why the restriction is onto. Is it because we are in finite dimensional cases, or?
No, we don't even need that. So let me point this out. So suppose let's let sigma. Now look at sigma restricted to E. Now sigma restricted E takes E and E because
Is still,
E is stable. Let me point out that sigma inverse restricted to E also takes E to E. Now, I think the concern here, now tell me, yeah, the concern here is maybe sigma E is strictly contained in E, right?
but that's also an automorphism. I see that. But that's also an automorphism, right? The inverse.
Okay. And so suppose that there's some stuff left over, right? Suppose that stuff can be mapped back into E, then you compose it again and you get contradiction, right? So I claim, so we know that sigma, let me drop the restriction here, just for my notation. Suppose sigma E strictly contained in E, right? Let X be in E, but not in sigma E, right? Now run it backwards. Notice that sigma inverse X is in E, well, equals E in E, because of this, right? So if I look at, if there's something if there's something here that's left over in E, say X, when I do sigma inverse to it, it has to be in E, right? And so now compose this again, and I get sigma inverse X equals sigma of E, and this is X, and this is sigma E, which is in E, and there's contradiction. All right. So, in other words, this thing has to be octave. Right. So, notice that the kernel of F, what is this? This is the set of sigma, such that sigma for E is the identity on E. The identity function on E. Maybe I should make that a fancy bar or something.
It's just all E out of.
Right. So this is actually, this is the set of everything that fixes E, right? So this is the Galois group of F over E, because it's all automorphisms of that to fix E. There you go. Now apply first isomorphism. Because you know what the image is and you know what the kernel is. Okay. So so this does it really. Let me make some remarks to kind of, for you to kind of cogitate, see how this puts pieces together. So, and then I'm going to make a more general statement. If E is an intermediate field, yeah, intermediate field. Say here if I could. So K is E is squeezed between K and F, such that E is Galois over K. Then what is to say? E prime is Galois over K. Since E and E prime are closed, C and E prime are closed, and G prime equals K. Right, that's from the fact that K is Galois. We have that the size of G mod E prime this is equal to the index of E prime and G, which is D double prime. Now remember these fields are closed and this is E over K. That's K and E double prime is itself. And so essentially the upshot of this is G mod E prime is mod Galois group F over E is isomorphic to because this is the subgroup of the Galois group of the appropriate order. That is the dimension of E over K. And so let me give you the following theorem. 18. 8.18. Suppose F is a field and G is a group of automorphisms of F. So suppose we just start with some field. So you pick some field. And suppose you happen to have a group of automorphisms of F. I didn't, by the way, I don't say all the automorphisms, just some collection that forms a group that will be the subgroup of the group of all automorphisms of F. And K is the fixed field of G and F. So you take your group of automorphisms, whatever they happen to be, and you just figure out what the fixed field is, right? So here's a dorky example. If your group of automorphisms is the identity, then the fixed field of that is just all of that, right? But whatever that group of automorphisms is, just compute what the fixed field is. Then F is Galois over K. And this is by definition, because so what does it mean to be Galois over K? It means the fixed field of the group of automorphisms is the base field. Well, we force that condition upon it. So F is Galois over K. And if G is finite, then F is finite dimensional over K. Okay, with Galois group. So in other words, if you start with any field you want, you collect a group of automorphisms and compute the fixed field, then F will be Galois over that fixed field. And if your group of automorphisms is finite, it will be a finite dimensional extension of that fixed field with Galois group G. Now, how many of you can compute a Galois group? Right? But we're going to get to that, right? Because I've told you a lot about this, I guess, and we've proved that this theorem, but I'm going to also show you a little bit later how to really get your hands dirty and figure out what these things are. And actually, I will also give you, so this is just like a security blanket. I'm like Linus and Peanuts carrying around this little security blanket, because I'm going to show you a way that will work to compute any Galois group over a field. Well, let me rephrase, over Q. So you can always do this. But I would never do it, right? Because it is so computationally a mess that, you never really do it by hand. But I'm going to show you some tricks to computing Galois groups, show you how to find some things out, and then I'll show you something that will always work over Q. But before that, we need to look at some other stuff. And this is where people care about Galois groups. So here's the playground. We've done this in a very kind of general setting. I want to look at some kind of applications, if you will, of this. Okay, so living fields and algebraic closures. How many of you have encountered algebraic closures before? You might have heard it. How many of you have ever had a class in algebraic geometry? Maybe, probably not. For example, a lot of the nice theorems in algebraic geometry is they assume that, well, I've seen lots of theorems where they'll assume that the field is algebraically closed, or at least close to algebraic. The reals are almost algebraically closed in a certain sense. So kind of as an C, well, every polynomial in QX has a root. How many of you are familiar with this? Every polynomial in Rx has a root. Now, of course, what this means is you can't always factor polynomials in Rx down to linears, can you? Right? I mean, you can have something like x squared plus 1, or you could have x squared plus 5x minus 1, something like that. Well, let's see. I guess that would be okay. X squared plus x plus 5, for example, will have no real roots. But if you throw in the complex numbers, then every polynomial reals you can factor down into linears, right? If you're allowing the complex numbers, you can factor every polynomial down into linear polynomials, right? And Q, of course, is much worse. The real numbers, the irreducible, what do you know about irreducible polynomials and reals? I think this was originally due to Gauss, actually. Real polynomials always factor into irreducible, well, in any polynomial ring over a field, you factor into irreducible polynomials, right? But in the reals, what do the irreducibles look like?
Linear, quadratic.
They're either linear or quadratic. There is no irreducible cubic or higher, right? Everything factors into a product of irreducible linears and irreducible quadratics. And that comes from the fact that basically you can prove that if you believe that if you have a complex root of a real polynomial that's not real, it's conjugate. Its complex conjugate has to be a root. And from that, you can deduce that everything is products of linears. By the way, if that were not the case, there would be one less section in Calc 2, right? Because the whole premise of partial fractions is that you can do that, right? Because what do you do in partial fractions? You take some polynomial and it boils down being able to integrate stuff like this. This is here squared. A squared minus 4b less than 0. Nobody would do partial fractions if the reals were as bad as the rational numbers, because there'd be too much to do. Because unfortunately, the rational numbers has irreducible polynomials of every degree, right? Whereas the reals only has irreducibles of degree 1 and 2. And so theoretically, if you can factor things down into linear powers and irreducible quadratic powers, then you can do all this. This is a bunch of, this is a U substitution, and this is completing some square root and doing a trig substitution, and there you go. But there's something that's more economical in the following sense. Suppose I wanted to go to the most economical field. So everybody knows this, right? That if I walk up to you on the street and I give you a rational polynomial, it's got a complex root, right? And so that means if I'm going to throw the complex numbers at it, then I can take any rational polynomial and factor down into linears. Be very proud of myself, right? But the complex numbers is huge overkill, right? Now you need a big field to be able to factor all the rationals down into linears, but you don't need the complex numbers. Complex numbers is humongous. It's got infinite transcendence degree of the rationals. It's bad. It's huge. You can actually have this property for a countable field, which is the algebraic closure of the cube, right? And so instead of, you know, throwing a nuclear weapon to kill an ant, why don't we try to do something a little bit more efficient? And this is the idea behind splitting fields. How many of y'all have ever heard of a splitting field? Heard that in the, yeah, so that's like part of folklore. Definition. So let's start off with this definition. Let f of x be a polynomial field at positive degree. Oops. Degree full f is at least 1. We say f of x splits. Let's see, over or splits in this field or splits over this field if f of x can be written as a product of linear polynomials.
Splits over f.
What's that?
What field are we splitting?
Yes. Over f, yes. Well, actually, we do this. How about it? That's the distinction I'll make. I'll say it splits in the polynomial ring, or it splits over the field. With U, R1, R2. So really, what did I do here? I looked at f of x, u is its leading term, so I jerked u out, and now I've got a monic polynomial. And if it factors down into a product of linears, then we say that the polynomial splits. Now, polynomials may or may not split, right? I mean, and whether it splits or not, I'm sure this is no surprise, depends on the field. X squared plus 1 splits over C Z2 and Z5, but not over Q, the reals, or Z3. By the way, just for giggles, and any of you in Robert Dix's number theory class? So he would give me a little gold star for asking you this. Does anybody know the pattern or the finite fields or the Z mod P fields that this splits over? This splits over ZP precisely when -1 is a square in ZP. So it splits if P is 2 or P is an odd prime that's equivalent to 1 mod 4. And this remains irreducible, that is -1 is not a square if P is equivalent to 3 mod 4. So you see, whether or not something splits, well, that depends on what field you're in. So let me, I got all excited. Let me sort of give a continuation of this definition here. We say that F inside F prime is a splitting field. So F prime is a splitting field for F of X and F of X. So this F of X could be different than the one over here. So this is just some general polynomial. If, number one, F of X splits in F prime X. So number one, if the polynomial actually splits, because it wouldn't be very smart polynomial splitting field otherwise. And two, right. That last one, the second condition is just kind of an economical condition, right? So a splitting field must be where the polynomial splits, and it is the smallest field possible containing F in which this field splits. So if F of X has roots R1, R2 up to Rn, notice that F is the smallest field that contains the original base field F and all the roots of the polynomial. So for example,
The second,
what's that?
the second condition doesn't imply the first one.
Yes, it does. It does. Example. Let's let F of X equal X squared 1. The splitting field of F of X over Q is notice the polynomial x squared plus 1 does not split Q. 2 of f of x over the complex numbers is C adjoining I, negative I, which is just C. So it already splits in the complex numbers because all the roots that you need are already there. Right? So when I talk about a splitting field, I need for the polynomial to split, but it's as economical as possible. And Pedro's observation is correct. Really all you need is this, right? Take whatever the base field is, dump in all the roots, and that'll be your splitting field. Yes?
In terms of sets, what is F prime? Is it like a subset of the algebraic closure or?
Well, I mean, yeah, that's what it's going to turn out to be. So F prime, so for example, in this case, you can build F prime step by step because really what QI is QX modulo. But of course, it can get more complicated. Let me give you another example. This will probably help illustrate some things too. Splitting field over Q, say, for this polynomial is a big friend of mine. What happens here? Well, what are the roots here? In this case, well, I know the splitting field is bigger than Q, right? Because this polynomial is irreducible over Q, right? In this case, R1 is cube root of 2. R2 is cube root of 2 times omega. And R3 is complex conjugate, right? Now, here's what happens. Let me just, and of course, it doesn't matter which way you do this, but the easiest way to see is this, well, you only dumped in one of the roots here. Actually, you only need to dump in one before. But here's what's happened now. This polynomial, well, you cracked it, but you didn't completely split it. It's sort of like the Liberty Bell now. This is x minus cube root of 2, x squared, 4, and this is going to be, yes, plus, right? Notice that cube root of 2, now you got a linear factor, but notice this thing actually doesn't factor anymore because if you do the quadratic formula on this, you'll get a negative discriminant of the radical. So this polynomial, you winged it, right? But it's still limping along, and you got to make it split all the way down. And so let's put in another root. And actually that does it. Because once you get this, then you also get the complex conjugate, right? Because basically in any field that contains this and this, it contains the quotient. So this, you've got omega in here. And if you got omega in here, all you got to do is square it and get its complex conjugate. So this is actually cube root of 2 omega. So here's what happened. And now what happens here is x cubed minus 2 is x minus cube root of 2, x minus omega cube root of 2, x minus omega bar cube root of 2, and we have success because it splits all the way down. Right? And notice you can do the step-by-step in algebraic construction. This thing is q of x modulo this polynomial. And now this one right here is q adjoined with the cube root of 2x modulo this irreducible polynomial here. Notice you actually had to go through 2 of these steps to make it factor all the way down. Okay, that's a good place to quit. Any questions on that? Questions? All right, well, you all have a good one, and we will catch you on Wednesday.